We hear constantly about scaling up solar power, but how does all of that intermittent, totally weather-dependent energy actually integrate into the grid without causing, well, total chaos? Welcome to this explainer. Today, we're breaking down the actual engineering and control systems that make this massive integration possible. We're going to look at some really fascinating research and simulation data that shows exactly how grid-connected photovoltaic, or PV, systems use battery storage to literally keep our lights on.
Okay, let's dive into this because this right here is the fundamental headache for grid operators worldwide. Think about it. We expect electricity to be there the exact millisecond we flip a switch, right? But solar panels only produce power when the sun is actually shining. So if a massive cloud rolls over a solar farm, the power output plummets instantly. And without a rock-solid plan for that sudden drop in energy, the entire system can become dangerously unstable. It is a high-stakes, real-time balancing act of supply and demand.
So here's our roadmap for today. First, we'll cover the solar intermittency problem. Second, the architecture of the solution. Third, controlling the power flow. Fourth, simulating real-world conditions. And finally, performance and future grids. Let's start right in with Section 1, the solar intermittency problem. The harsh reality is, just slapping a bunch of solar panels on a roof simply isn't enough to power a stable modern grid. Intermittency is not just a minor inconvenience, it's an absolutely critical threat to grid stability. When solar irradiance fluctuates because of the weather, the power output of a PV array fluctuates right along with it. In a traditional power grid, this sudden loss of generation causes the voltage to sag and the grid's frequency to destabilize. If generation and demand become dangerously mismatched, you're looking at brownouts or even complete system failures. It's kind of like trying to maintain steady water pressure in your house while someone keeps randomly turning the main water valve on and off. So, to manage this, the system relies on something called MPPT, which stands for Maximum Power Point Tracking. You can think of this as the brains of the solar array. The output of a solar panel changes based on temperature and how much sunlight is hitting it. An MPPT controller uses algorithms, like one called Perturb and Observe, to constantly tweak the electrical operating point of the panels. It's essentially hunting for this mathematical sweet spot to make sure the system extracts the absolute maximum amount of energy available at that exact second. But capturing the energy is only half the battle. Now we actually have to move it and store it. Which brings us to Section 2, the architecture of the solution. Think of these hardware components as a highly specialized relay team passing a baton. Step 1 is our PV array, the raw energy collectors. Step 2 is the bidirectional DC-DC buck-boost converter. This guy acts as the traffic cop, stepping the voltage up or down exactly as needed. Step 3 is where the real magic happens, the DC link capacitor and the battery energy storage system. This is our crucial energy buffer. And finally, Step 4 is the grid-tied inverter, which takes that stored DC energy and translates it into the perfectly synchronized AC power that the utility grid actually uses. Now, what's really interesting about this slide is the dynamic bidirectional nature of the setup. When the sun is just blasting what we call high irradiance, the system prioritizes charging the battery. It acts as an energy sink, soaking up power until it hits about a 95% state of charge, and then it smoothly redirects all that surplus energy out to the grid. But what happens when a cloud rolls in? Or the sun goes down? The traffic cop flips the flow. The battery discharges, instantly stepping in to support the DC bus and ensuring the grid literally never feels the loss of the sun. But how do all these separate hardware pieces know exactly when to charge, when to discharge, or when to send power out? Let's look at Section 3, controlling the power flow. The secret lies in one very specific number, 905 volts. In the system analyzed in our sources, the engineers carefully regulate the DC bus voltage, that's the central hub connecting the solar, the battery, and the inverter, to exactly 905 volts. However, the system's internal reference target is actually set to 900 volts. So why hold it at 905 when the target is only 900? Right, so the crucial point here is that tiny 5-volt difference. This intentional offset acts exactly like a pressure valve in a plumbing system. By constantly keeping the actual voltage slightly higher than the reference voltage, there's a continuous electrical pressure. As the system's regulator tries to reduce the bus voltage down to match that 900-volt reference, it actively forces the extra current to flow outwards into the utility grid. It is a brilliant, completely passive engineering trick that guarantees surplus energy is always safely and efficiently distributed outward, preventing the whole system from bottlenecking. But theories and clever pressure valves are great on paper. Do they actually hold up when the weather turns unpredictable?
Time for Section 4, Simulating Real-World Conditions.
To prove this works, researchers built a highly detailed model using the MATLAB and Simulink environments. And they didn't just test it on some perfect, sunny, hypothetical day. They subjected the digital twin of the system to rigorous, real-world constraints. They varied the solar irradiance drastically, going from a gloomy 200 watts per square meter all the way up to a blazing 1,000 watts per square meter. They also tested it with the battery nearly empty at 20%, all the way up to fully charged at 95%. And this brilliantly illustrates the system's adaptability across 3 distinct scenarios. In case 1, with a constant, perfect 1,000 watts per square meter of sunlight, the system pumps out a stable 30 kilowatts of power, charging the battery and feeding the grid beautifully. In case 2, we simulate a passing cloud, dropping the sunlight to 600 watts per square meter. The solar output drops to 18 kilowatts, but the system instantly adapts by reducing the battery charging rate to compensate for the loss. And then in case 3, a heavy overcast day, below 400 watts per square meter, the solar panels just can't sustain the grid alone. So the battery automatically switches into discharge mode, pumping its stored energy out to maintain that vital 900-volt stability we talked about. Actually, let's zoom in on that second case for a second, because the speed of this system is truly staggering. When that simulated cloud rolls over and power generation plummets from 30 kilowatts down to 18 kilowatts, chaos could so easily ensue. But that MPPT controller, it instantly tracks the new maximum power point. The system experiences what engineers call transient oscillations, basically a brief moment of electrical wobbling. But the system corrects itself and settles completely in under 50 milliseconds. That is literally less time than it takes you to blink. The grid doesn't even notice the sun went away.
Let's wrap up with Section 5, Performance and Future Grids. So we've seen that the system can handle the intermittency problem incredibly fast. But what is the actual quality of the power it's delivering to our homes? Well, the quality of AC electricity is measured by something called total harmonic distortion, or THD. This simulation proved that the inverter system keeps THD under 3%. That is incredibly clean power, fully compliant with strict IEEE 1547 standards. What that means for you and me is that the energy flowing from this solar and battery setup into your TV, your refrigerator, and your laptop is as stable, if not more stable, than traditional fossil fuel power. So, we know integrating localized battery storage works flawlessly to stabilize solar power. The catch? Scaling this up requires massive batteries. Which brings us to the bleeding edge of grid research, vehicle-to-grid, or V2G technology. Think about it. Instead of building massive, wildly expensive battery farms, what if we used the millions of giant batteries sitting parked in our driveways right now? By integrating machine learning algorithms with this exact bidirectional converter architecture we just explored, your electric vehicle could charge when the sun is shining and discharge to support your local grid when a storm rolls in. So the smart grid of the future might not just be on your roof, it might be parked in your garage right now. Something to think about. Thanks for joining us for this explainer. We'll see you next time.